You know that feeling when you type a prompt into ChatGPT and boom, it instantly spits out a brilliant essay or perfectly writes some complex code? I mean, it genuinely feels like magic, right? It feels like there is this omniscient, all-knowing brain sitting right behind that text box. Well, welcome to today's Explainer, where we are going to completely break open that black box of artificial intelligence. Today, we're stripping away the illusion. We're going to look under the hood and discover that, well, there is no magic. Instead, there are billions of mechanical, statistical token tumblers just churning away. By the end of this, you are going to understand exactly how large language models go from just raw, messy data to the seemingly intelligent assistants we use every single day. So here's our game plan for this explainer. First, we'll demystify the magic. Then we'll walk through the actual training stages, pre-training, post-training, and reinforcement learning. And finally, we'll dive into the psychology of AI.
But before we get deep into the mechanics here, I want you to consider a pretty wild paradox. Why is it that a large language model can pass the bar exam, write an intricate Python script, or explain quantum physics to you, but if you ask it to simply count 20 dots on a page, it completely fails? Or, why does it struggle to tell you how many R's are in the word strawberry? It makes no sense, right? Well, we are going to resolve these sharp edges today, and the answer actually starts right at the very foundation of how these models are built.
All right, part one, demystifying the magic and seeing like an AI. To really get this, we have to fundamentally unlearn how we think about reading. Because large language models, they do not process language the way our human eyes do. They literally don't see letters or words. Instead, they rely on a process called tokenization. So tokenization is this mathematical process of taking raw text from the internet and breaking it down into a finite set of numerical chunks. Remember, neural networks run on math. They can't digest an A or a B. They need numbers. So researchers compress all of human language into roughly 100,000 unique numerical symbols. You can almost think of these tokens as unique emojis that make up the AI's entire functional universe.
Let's think about what this looks like in practice with a classic phrase, hello world. To an AI like GPT-4, that is not 11 letters. It is exactly 2 tokens. It sees token ID 15339, which maps to the word hello, and token ID 1917, which maps to world with a space in front of it. It has absolutely no concept of what an H or an E is. It just knows 15339. This one-dimensional sequence of numbers is literally the only thing the neural network ever looks at. Keep this tucked away in your mind because it is the absolute secret to unlocking why AI struggles with some really basic tasks later on. Moving on to part 2, pre-training and building the base model. To ground some of these heavier technical concepts, let's use a framework we all know, going to school. In this AI curriculum, the pre-training stage is basically the equivalent of locking a student in a room and forcing them to read every textbook, encyclopedia, and web page ever written. They aren't answering questions yet, they're just absorbing raw information. Later on, post-training will be like showing them expert solutions, and reinforcement learning will be their practice exams. But right now, in pre-training, they are just reading.
And when I say they read everything, I mean it at a scale that is honestly hard for the human brain to comprehend. 15 trillion. That is the number of tokens in a standard, publicly available dataset like FineWeb, which is used to train these models. 15 trillion. The model processes those tokens across thousands of massively expensive computers for months at a time. And what is it doing that whole time? It is simply playing a massive, endless game of autocomplete. It looks at a sequence of tokens and guesses the very next token. If it guesses wrong, it mathematically adjusts its billions of internal parameters, kind of like turning tiny precise knobs on a massive DJ board, so that its next guess is just slightly more accurate. So, what do we actually get at the end of this massive multi-million-dollar pre-training stage? We get what engineers call a base model. But here's the catch, and it's a big one. A base model is not an assistant. You can't just ask it to help you write an email. As the prominent AI researcher Andrej Karpathy describes it, the base model is essentially a lossy zip file of the internet. It's just a massive token simulator. If you ask a base model, what is 2 plus 2, it might reply with, what is 3 plus 3, what is 4 plus 4, because it's just predicting what text usually follows a math question on an internet forum. It has vast, incredible knowledge locked inside its parameters, but it literally doesn't know how to be helpful yet.
Which brings us to part 3, post-training, where we actually build an assistant.
So how do we transform this unpredictable internet document simulator into a helpful, truthful, harmless instruct model? Well, we bring in human teachers. During post-training, human labelers literally write out tens of thousands of perfect conversational examples.
They'll write a prompt like, help me write a resume, and then they meticulously write out the absolute ideal response. We essentially swap out all that messy internet data for this pristine, highly curated conversation dataset. The model trains on these examples and rapidly learns to imitate the persona of a helpful human expert. So when you're talking to ChatGPT, you aren't talking to some magical consciousness. You are talking to a highly refined statistical simulation of those expert human labelers.
Next up, Part 4, Reinforcement Learning, because practice makes perfect.
In this final stage of training, we force the model to start thinking out loud. We give it practice problems, like a complex math equation, where we know the final answer, but we don't hand the model the step-by-step solution. It has to figure it out on its own. And this reveals a totally fascinating mechanical limitation of AI. You see, a neural network only has a fixed, finite amount of computational power to spend on every single token it generates. If you ask it to solve a massive math problem and output the final answer in a single token, it will fail. It literally just doesn't have the processing time. So by forcing the model to print out step 1, then step 2, then step 3 across hundreds of tokens, we are essentially allowing the AI to distribute its computational workload across time. It calculates intermediate results, stores them in its own text, and then uses that very text to finally arrive at the correct answer.
Finally, Section 5, the psychology of AI.
Now that we understand this engineering pipeline, all those weird cognitive quirks and behaviors these models display suddenly start to make a lot of sense. Take AI memory, for example. You've got the model's parameters. That's all the knowledge it absorbed during its pre-training. But you really should think of parameters as a vague recollection. It's kind of like asking you to summarize a book you read 5 years ago. You'll definitely remember the main characters, but you might confidently hallucinate the exact details. Then, on the flip side, you have the context window. That's the text box where you actually type your prompt. The context window is the AI's working memory. It is like having that book open on the desk right in front of you. This is exactly why, if you want a highly accurate summary of an article, you shouldn't just ask the AI to retrieve it from its parameters, you should paste the entire article directly into the chat window. When it's in the context window, the AI has perfect direct access to it.
And now we can finally answer that crazy paradox from the beginning of our explainer. Why does AI have these sharp edges? Why does it struggle with spelling, basic counting, mental math, and hallucinating facts? It all comes back to tokenization. When you ask an AI to count a line of 20 dots, it doesn't see 20 individual dots. Its tokenizer might lump all 20 of those dots together into a single random token ID. It is quite literally blind to the individual characters. And because its mental arithmetic is just statistical prediction, it makes silly mistakes. This is why it's absolutely crucial to let the AI use external tools. If you need it to count or do heavy math, ask it to write and execute a Python script to find the answer rather than just relying on its statistical brain.
Which brings us to our ultimate takeaway for today, perfectly summarized by a quote from the source material. Use them as a tool in a toolbox. Don't trust it fully, but use them for inspiration. Look, large language models are not magical oracles. They are incredibly powerful stochastic token simulators, and they require our active supervision and understanding to actually be used effectively. So the next time an AI hallucinates a weird fact or completely fails to count a row of apples, ask yourself, are you expecting magic, or are you ready to guide the mechanics?